Good evening, ladies and gentlemen. Welcome to Lecture 11 of Topic 2 of Unit 4, Rutherford's Atomic Model. And we're going to be covering the main ideas of Chapter 12.1 of Book 2. Please complete this reading before class. Here are the learning intentions and success criteria for the chapter. Please pause the video and attempt to complete the KS table down the bottom right corner. Okay, so we can see here it's a very knowledge-focused lesson. We're about describing Rutherford's model of the atom and explaining the limitations of the model. Now, the two criteria from the syllabus is that you have to be able to describe the model and describe the limitations. If you can understand what the explanation for the limitations are, it makes it a bit easier, in my opinion. So in terms of knowledge, you need to know what it is. If you don't know what it is, it's pretty hard to describe. And what are the limitations? So, in Year 9, we learnt about different models of the atom and how they progressed over the years. Now, for this topic, you need to know about 3 of them in order to explain how the evidence contributed to the development of the models. Now, the 3 models you need to know about are Thomson's Plum pudding model, Rutherford's planetary model, and the Bohr atomic model, which will be coming in the next video, 4.2.12. So they won't be covered in this one, just the first 2 in this video. So, the Plum pudding model. The syllabus doesn't need you to describe the model, but I feel if you understand this first step, it makes explaining Rutherford's model easier because you understand where they got from. So the plum pudding was developed after the discovery of the electron, or the plum pudding model. The dessert had been around for a while at the time. Thomson knew that the electron was small, but that the atom was neutral. It had no net positive or negative, so there had to be some positive charge across it too. And he figured that there was a distribution of positive charge across the atom, and these small little negative electron chunks distributed across the atom. So kind of like this, we've got a big ball of positive, and there are just these little negative chunks floating around inside. Our plum pudding is an English dessert that the model, this picture here, was thought to look like, hence the name, but an easy one for you to imagine in the 21st century might be that, think of it like a chocolate chip cookie, where the electrons are the chocolate chips, and the rest of the cookie is the positive part of the atom. So, Rutherford came on the scene, and he had the model from Thomson, and he wanted to test it by shooting alpha particles, which he knew were positively charged. He didn't know what they were made of, as Marie Curie had yet to do her studies on radiation and radioactive decay at this point, but they knew they were positively charged. So he shot them at a thin strip of gold, and the setup looked a bit like this. So here's his alpha emitter, and here's his thin strip of gold, and he just shot them at the gold, because you can get gold very thin, so a couple of atoms thick. His hypothesis was that if Thomson's model was right, the alpha particles should just go straight through. Sorry, mosquito. But instead they deflected. Okay, we see them deflecting here, and some even bounced back. You can see some went straight through, the ones there in the middle, but then a lot of them bent off to the sides, and then a few over here bounced back. And he used this evidence to reason that instead of a positive charge being spread out, it was condensed in the middle like an atom. Okay? The nucleus. So, condensed in the middle of an atom, which was the nucleus. And the electrons were whizzing around it like planets. Okay, so in terms of a picture, this is what he's got here. So these are the main features you need to have, that there's a tight, small nucleus in the middle that's positively charged. There are electrons going around it, they're negatively charged, and the electrons all have an orbit around it. Now, do notice, compared to the model that you probably saw at the end of Year 9, and you might be a bit more used to, especially if you've done some chemistry, is that these orbits here are just whizzing around, overlapping each other. This is a very common picture often seen on nuclear power plant type things. The Simpsons, you've probably seen in The Simpsons. But it doesn't show those nested shells like we've seen, and we'll see that in Bohr's model next. So this was Rutherford's model, but there were problems with it. Maxwell's equations, he did a lot of work on electromagnetism, but Maxwell's equations predicted that an accelerating charge particle would emit electromagnetic radiation. so that the orbiting electron should have to give off electromagnetic radiation. It would have to give off energy. But if it gave off its energy, it would have to slow down and collapse into the atom, okay, into the nucleus. The math predicted that that would happen in 10 to the negative 8 seconds, but it doesn't. In the time it would have taken me to read this sentence, all the matter around us, around you, around in the Earth, would have collapsed and turned into neutrons or maybe exploded. Now, that hasn't happened, because from what I can tell, my office is still here and my tablet's still in front of me, so there must be a problem with this model, because Maxwell's laws were very, very clear-cut and mathematically proven. Okay, the atomic model hadn't been, still had issues with it. So while they knew bits, they still didn't have it all put together. But Maxwell's laws, they were pretty rock solid. The second problem was one called was about atomic spectra. Now, and that's the particular colours that gases emit when they get hot enough, or they absorb when white light is shone on them. The model of the atom just couldn't explain it at all, and hydrogen here emits 4 distinct colours. Okay, so there's no explanation within Rutherford's atomic model that said this is why this happens. So let's talk about atomic spectra a little bit. Now, scientists had known about atomic spectra at this point for a little bit. Hydrogen gas, they knew, emitted 4 visible lights. So if we take some gas, we shine it through a slit so that it's collimated and all go in the same direction, and into a prism, the different colours will refract a different amount, and so the red light, the blue, green, the blue, and then the violet, and you can see here their wavelengths. So this information was known. It was very well catalogued and very well recorded, and they knew about this, and they knew about it for other gases. They'd been working on it since the early 1800s, with some focus on gases in the 1850s. So they knew different elements had their own different spectra, but there was no why. Apologies, I had to cough. This is hydrogen spectra, and you can see here the 4 visible, this is the emission spectra, see the 4 visible lines, red, the blue, green, the blue, and the violet. Now this is one here, is another violet one, that's a very high energy level. When we talk about shells, that happens when an electron drops from the 7th shell, which is a lot of energy. And you can see here, this is the absorption spectra. So if we shone white light onto this hydrogen gas and we looked at what came through it, everything would come through except those 5 bands. So for the hydrogen spectra, there's a little bit of extra detail we want to give here, and we'll use this information next video. But a scientist named Balmer worked on hydrogen emission and worked out an equation that would model the visible lines very well. He didn't have a why for it, but he did have some information. Now, the textbook goes into this in a little bit more depth. You don't need to know about Balmer's work, but recognizing the name will be important. We'll see that next video. But Rydberg was another scientist who worked on this, and he cleaned up the equation into this form, and it's provided in the formula booklet. We will use it next video, and this is sort of showing it here to conclude where it goes. So this were the issues. They knew that the center of an atom, where the nucleus was, or the reason that there was a nucleus, was small and positive. They knew the electrons orbited around it, but there was a problem with the orbitals, and there was a problem with this idea of emission spectra. And then Bohr came along, and this is Bohr here, and he fixed it. And we're going to look at his work in the next video. He used Rutherford and Planck's work. He won himself a lifetime supply of beer, from what I've heard as well. So he did get a Nobel Prize for it, and we'll have a look at his work in the next video. So in this video, we have learnt the following. We have looked at Rutherford's experiment and how it disproved Thomson's model, and then we've described Rutherford's model and described the limitations with it. Okay, so while that first point you don't really need, because you can see here Thomson's not mentioned, if you know where it's come from, it's a bit easier to explain the next step. Okay. So for your entrance slip to class, please complete questions 1 to 3 in chapter 12.1, check your learning, and copy your answers for those into the 4.2.11 space on eLearn. Thank you very much for listening, guys. Have a great evening. Bye.